Probably December 2.
All right, we're going to get started. So we'll start with some announcements here. As most of you know, proposals, series submissions are due today. Make sure you do put your name on it and your group number and the name of your project so that when I print them out, I know what they are. That's helpful. But resubmit them today. We'll grade the final version, not the first version. Homework 7's assigned. It's due next week. That will be your last homework assignment. The exam is scheduled for next week. And then we're going to start student presentations after that. So last night I went through and assigned each of your project teams a topic. So you should go check through here and see, this is linked on the assignment page. There's a description of the assignment, which is basically you are going to research some aspect of embedded systems that's been assigned to you and do a 12-minute to 10-minute presentation to the class, teaching the rest of your classmates about some idea. Now, I tried my best to give you something that's actually related to your project. If I failed at that, I don't know, you're not using LiDAR on your project, you should let me know. I'll switch it around for you. I also tried to group these ones that most people will need in the beginning. So driving a brushless DC motor or a DC motor, how to do that. That's lots of groups are going to need that. So we put it up front, PS2 controller, XB, a graphical display. So these are going to be on the first day, that Monday after we get back from, after the exam. Oops, come back. So here we are. We're here. Next week is a review. We'll talk about DMA and PCBs design. Then you'll have your exam. Then we'll start student presentations. The student groups need to come and practice with me, Matt, or James beforehand. So we're going to make a sign-up schedule. I'll post it tonight. We'll give special priority to especially this group. I'll make some times over the weekend and next week, so that make sure that you guys get a chance to present. Everybody else needs to present or do a practice presentation, before their presentation. Any questions?
What the component?
Yeah. No questions. Good question.
For the component for the presentation, is it just the one main component, or do you have to do all your components?
No, just one. But you're going to be a little bit deeper dive, right? So it's going to be so people doing motors and motor drivers, it's not just you want to give some background of how does a motor work, right? And then it's well, how would an embedded systems person drive that thing? So how do you go from your signals, 3.3 volt signals, to driving this motor, and then what are the control things you have to think about? So it'll force you, so I try to choose ones that are actually relevant to your project, because it'll force you to learn how to interface with this thing you've chosen, and it will teach other people how to use it.
Is that just class?
Yeah.
I don't know if it's for once I mentioned student presentations. The student presentation, is that us practicing with you guys or us presenting?
It's both. You're going to first practice with me, Matt, or James, and then you're going to present in the class.
Basically set up for 2 slots. One is to practice.
Well, you've been assigned a slot, so these days during the class you have student presentations. You've been assigned a slot. That is denoted here. Presentation day, slot, number. There you go. And then beforehand, we'll have a sign-up sheet for you to come and practice with us.
So the training we're signing up for is our practice, since our actual presentations are.
Yep. I just didn't get a chance. I have not agreed with Matt and James about all the days for your practice. Do you have a question? Nope.
Oh, yeah.
So this is online. You can go look it up. You don't have to squint. It'll be just fine. All right. Any other logistics questions about what's coming up? Zero questions. Fantastic. Okay. So I didn't quite finish off the ADC slides. I did want to talk about the ADC that you have on your STM32. And by now you should be able to more or less navigate your way through this block diagram. So here's your SAR ADC. It has some We'll talk about these things, but injection channels and output channels and oversampling modules. So you should be able to read through the documentation, because you guys should be getting pretty good at reading the data sheet by now, and kind of work your way through this diagram. But high level, you get a 12-bit ADC that runs at 5.3 megasamples per second. So that's pretty fast. And because it's a SAR ADC, you can reduce the resolution and get up to 8.8 megasamples per second. I don't know exactly when I would need to do that. I mean, obviously, if it was sampling something really fast, but there is the option. They have this idea of channels. So it has 16 external channels, which means these are analog pathways that go and lead to your DAC, that lead to your digital GPIO pins. And so now you can sample up to 16 pins on this microcontroller can be converted or configured as analog inputs. And then those will be fed into your SAR ADC. There's also internal channels. So there's an internal voltage reference. Why would you want an internal voltage reference? Why would you? Does anybody think about why you'd want to measure some internal voltage? Yeah.
Just like a step like the DAC, change, I try to find a value.
You could do that. Any other ideas? It's not a bad idea. So the internal voltage reference is a very stable voltage reference. It's called a band gap voltage reference. And basically, it gives you a known value. And that will be a known value independent of your input of your power supply voltage. So if your power supply voltage is kind of noisy, or maybe it's varying, there is a range at which your microcontroller can be powered at. This thing will say, this is my actual internal voltage. It's, I think for you guys, it's 2.7 volts. And therefore, you could measure your internal voltage reference and be like, oh, wait, something must be weird here because I'm measuring this, and I'm supposed to be getting this DAC value, but I'm getting some other DAC value, right? So now you have a way to calibrate your ADC. Sometimes I don't know if you can do it for this particular microcontroller, but sometimes you can run the reference, see the bias, you can do it. The bias voltage can be run off of your internal reference voltage. So that means that you're going to be more independent of noise, although you're not going to get your full range. Other internal references, or other internal things that you can measure is that there's a temperature sensor. So every piece of silicon can be made into a crude temperature sensor. Basically, you take two diodes of the same size and run two different currents through them of known values, and then the voltage difference between them is going to be proportional to absolute zero. So you can get within 2 or 3 degree accuracy pretty reasonably well with just any piece of silicon. So you can always just think to yourself, in the future, if I need to know temperature, my microcontroller should probably already do it as long as it has a DAC. You can look at your battery voltage divided by 3, and then you can actually look at your DAC voltages. So we'll talk about DACs next, but internally they'll route the output of your DAC into your ADC so you can double check, is my DAC doing what I expect it to be doing? And then there's also an opportunity here to have 16-bit hardware oversampling. So now you could, you have this accumulator, so you take a sample, and then it will do the averaging for you, basically. So it will keep on sampling data, and then when it's, you get your 16-bit oversample, it will throw an interrupt, and then you can pass that on to your output channels. And then it has 3 watchdog channels, which is kind of interesting. So we have watchdog timers, and I don't remember if we talked about them, but a watchdog timer is a timer that must be it's a register. You set up the timers. You have to read to the register before the timer goes off, or the system forces you to power on reset. Does anybody know why that would be useful? Having some timer that goes off, if you don't schedule it, you reset yourself.
If you have a sensor and it's not working, maybe you reset it and it'll fix itself and start something again.
Yeah, but let's go back to the case of just a timer before we go to the analog one.
Maybe there's software or firmware can work.
Yeah. So you have some code in your thing that hangs the device. You have some unknown state. Well, you don't want your device to be hung forever, right? And then you have to have some technician go out and do it. So you have The watchdog timer, your main loop should basically go through every so often, whatever the interval is, and rewrite to that register, setting it back to 0, waiting for it to count up. And then if your software does hang for whatever reason, the hardware timer, the watchdog timer will go and then power on reset you. So this is a way to kind of save your device and not have to deal with field reinstalls and angry customers. They have a similar idea. That's just the idea of this watchdog. And then an analog watchdog would say, hey, I'm measuring this value. I have an analog value that goes between a certain range, maybe let's go between 2 values. And if it ever goes above or below that, then throw an interrupt. So you can just send your ADC off to do some task. And maybe it's a distance sensor where a value goes high when something's too close. And then it just continuously runs this ADC. Your core can do whatever it wants. It can go to sleep. That's typically what low-power microcontrollers are trying to do all the time, save power. And then if it goes high enough, it'll go and throw an interrupt that will cause you to be able to respond to that event. We talked a little bit about sample and hold circuits. So on your STM32, there's a register to select what your number of cycles for your sample and hold. So the minimum here is 4 cycles, and that is dependent on what is the clock going into here. So you can have a 16 megahertz clock, and you can divide it by some prescaler, and then off of that intermediate clock, you can go through and choose how many cycles you want for your to charge up your sample and hold circuit. So in this diagram, here you have the sample time, and then you have your conversion time. So we're saying that this is software selectable. And why does anybody remember? I know everybody's looking at their things, they're not very excited, that's fine. I get it. Does anybody remember why in the world you'd want to change your sample and hold time? Why don't you talk with your neighbor, figure out if you guys can remember, or just look back on my slides to figure out why you'd want to change your sample and hold time.
Just take a certain amount of time to get value. So you may want to delay. It's like it's that you're
What do we think? Why would we want to change our sample and hold time?
Like save more power because you're holding on to it instead of sampling faster.
Nah, not really. I don't think I would just go as fast as I could then. Why would we ever want to go slower than the fastest possible? What's that? Does it yield power? What does that mean? What do you mean deal with power?
Like if you're sampling a lot, if you're doing a lot of like operations, activity.
True, but I could just slow down my sample rate then. I don't need a sample device for that. Yes?
For accuracy reasons.
Oh, you have to be loud.
For accuracy reasons.
In what way?
Like the longer you sample, the more correct you are. Or like the more resolution you can have.
No, I know there's an EE here. I see you. Why? Why? I know you're looking, maybe you'll find it. Why, if I had a signal, would I want to sample for a longer period of time? Yeah?
The signal may take a minute to get to a stable value.
Okay. Yeah, and what might cause this to occur?
Would you want higher resolution?
I'm getting towards source resistance. Ooh, this guy knows about source resistance. I know he does. Okay, so you can model your sensor. This is a resistor, and we're going to call this sensor. This has an output. This source resistance is going to limit the amount of current that can be driven into what? Well, it's going to be a capacitor. And this capacitor is what is being used. Remember, there's a little switch here. All right. You're going to store some amount of current on this capacitor. Some amount of charge, on this capacitor. And so if the resistance here is very small, well, then it's going to get charged up very quickly. Great, that's what we want. However, we don't live in this nice ideal world. Sometimes you have sensors that have high output resistance, and that will mean that you are charging slower and slower and slower. The higher this value is, the longer it takes to converge to some value before this capacitor will be charged up to VDD here, or V out of that sensor. So the source resistance is a serious problem, and by changing your sampling time, you can allow that capacitor to charge up to a different value. How's that work? Is that a good EE reason?
Makes sense to me.
Fantastic.
I don't know if I'm the expert. I think you're the expert, so.
No, I did. You've taken EE classes more recently than me. So all I'm saying is, why would you? So for the non-EE majors, the CE majors, and the computer scientists, why? Why would you do this? If your signal cannot be drive a value very quickly, if you put your thing on an oscilloscope and it takes a long time to charge up, right? Compared to the sample time, then you need to go and increase your sampling size. What do we think? Does that make sense? Yeah.
So in short, you're saying you want the ability to control sampling size to be able to match it with the effects of how quickly you can actually charge up your capacity.
Correct. Right? So you have some drive strength of this sensor. That sensor might have a poor drive strength. Now, in the reality, this capacitor is really small. I don't know, how big is this capacitor? I don't know. 500 picofarads, let's say, which is pretty small. And these things are probably going to be like, say, 50 ohms, which is pretty small itself, but you're trying to do it really, really fast. So you can calculate your RC charge up time for that. And you remember, you're trying to go up megasamples per second. So you want that little capacitor to charge up inside that thing fast. And those are just approximate numbers that I guessed at. I don't actually know any real numbers. Yeah?
Why does sampling time affect how much is charged up?
Well, you can't see anything because I put it way over there. I'll draw it over here. So if the resistance is small, source resistance is a great sensor. It'll charge right up. But if the source resistance was large, it's going to take a long time. And so if I set my sampling right here, for a small resistor, great. I've got the analog value, voltage, time. This is really close to my output voltage, great. However, I'm here. I've done the same sampling times, right? And that is not the end voltage here, right? So this is the voltage on that capacitor in your sample circuit. I sampled so fast that I didn't even give that capacitor time to charge up.
What is the source resistance?
It will be constant for a device, but it's not constant. Well, that's half true. It's typically constant for a device, but it's not constant for every possible sensor or every possible source. Some of them are pretty low resistance, or high resistance, sorry. Yeah.
I know usually the ADC or the DAC makes in mind with like buffering and like make a resistance smaller, like to help with like the difference.
Yep. You could put an op amp in there and make it faster.
So would there be a case where you're not really able to alter the sampling time, or you don't want to alter the sampling time, which is like kind of put some sort of op amp.
Yeah, you could put, the statement was, well, if this doesn't have enough drive strength, how could I solve that? Well, one way is you could put an op amp in there, and we could do a voltage follower. And so this should have low input, or should take a small amount of current, so it should have a high input resistance, and this should have low output resistance. So this will take this voltage and put it over here, and it should do it, be able to drive that capacitor much faster. Now it just cost you something. Right? It cost you this component on the board. Maybe you don't want to make that trade-off, right? So now you could just change something in software and allow for that thing to charge up. Okay. And then for your particular device, right, you can say here, I have a 60 megahertz clock and 4 clock cycles, and you could go through and figure out for a 12-bit ADC, how long does it take to sample something, or at least to converge. By the time you say go to converge, here you can just count through the cycles. What did I say, 12-bit? So 12-bit ADC is going to take on average, or it's going to take 6 cycles to converge, because you're doing a binary search. and now you're going to get to 625 nanoseconds. Yeah. Nothing? Okay. I'll just go through some options to make you aware. The output of your ADC, you can choose to control how the data is aligned. It's kind of an interesting thing. You can say if it's signed, not signed, and you can say how does it pack up that 16 bits. If you're just doing 8, then you could go and say toggle back and forth and double use that memory location. I don't know why you really need to do this, but every once in a while somebody gets confused about why it's even an option. And that's usually to do just data packing and make sure it's as small as possible. On your ADC, there's 2 different modes. There's this kind of regular channel mode where you'll have this MUX, right? So this is a GPIO port, and there's a MUX. There's only one ADC, even though you can have, on your particular device, there's up to 16 different analog pins that can be configured as an ADC. It just means that they're going to be time multiplexed. So this MUX is an analog MUX that's going to take this value and put it into the ADC. And in the regular mode, you have this regular channel. It's going to do a conversion and put it out here. If you want to go faster, you have what's called injection channels where it'll do 4 sequential reads, and they actually have their own location up here. So now you can store up to 4 ADC values before having to come out with DMA or an interrupt to do a task of taking that data and putting it somewhere. Yeah.
Why would you want to do that?
Why would you want to
do the injection? Like having those 4 significant values.
That's a great question. So it even gets weirder than that, right? So here, this allows you to go faster. And now because I don't have to go through and do a memory read each time, right? So memory's still pretty slow. Because you have to go, I think this is on the advanced peripheral bus, I don't actually remember, but it means you have to go through the high performance bus into the advanced peripheral bus, into this peripheral, and send the data all the way back to memory. It takes a long time, so we can do this. We have this option here. And here, it's interesting, well, do I have a slide on it? So the difference between injection channels and regular channels, injection channels are actually a higher priority, actually come up with higher priority interrupts. And so you could have multiple sampling thing, which is a weird idea. Why would I want an analog? I have one ADC. Why would I want an ADC to interrupt the task of measuring another ADC value? How does that even, why would you do that? Doesn't make sense. So how you set it up is you're going to set up these things might be your highest priority. Maybe you're sampling that a mega sample per second on some value that you need a very precise time frame for it. But then you have some other value, like a temperature sensor. We know from last lecture, temperature sensors aren't going to vary that much. Maybe once a second would be fast enough. So this is a lower priority than this. These will take priority, and it's not priority over the same digital I/O pin. It's that they're going to change the MUX. So one MUX might be to a temperature sensor, and then these other things will be to, say, the signal you want to sample, and you can have all 4 injection ports going to one particular pin. So now you're saying that this analog signal that's faster, you want high precision on, has the highest priority. So even if an interrupt comes that says do this task, or sorry, say you're doing this task, this thing can override that one and recontrol where the MUX is pointing to get that value. That's kind of talked about here, not really though. There's just different modes. Typically, you could be in software, you go say start, and just do a channel and then stop, and you can do it in continuous mode. And then the injection channels is just allows you to basically pipeline this action, do it as fast as possible, get those 4 reads out. Thinking back to this figure here, we have some voltage value that has to be corresponded to some digital value. And it's important to think, it's not a 3-bit ADC, it's a 12-bit or 8-bit ADC, but where does this voltage correspond to? Well, you can inject an external pin. You could have, externally, you could have a reference voltage that drives that. It could be the VDD pin, or it could be an internal reference, like we talked about before. So it's important to think about, as you're configuring it, it's not necessarily going to be 0 to 3.3. It could be some other value, and it's important to think about what is that top value of your ADC analog conversion value. Let's see, we talked about watchdogs already. Basically, it's just that there's a threshold. You can check to see if the analog signal wanders in and out of that. I don't really talk about low power in this class, but your MSP430, or no, sorry, that's the different project. Your STM32 has a low power mode, several low power modes, and typically for battery powered things, you want your microcontroller in sleep as much as possible. So a lot of an engineer's time is trying to figure out how to do other tasks while this thing is asleep. And if you're just trying to measure some, see if a value leaves a certain area, this would be a way to do it. So the intended structure, or not the intended structure, but a way to use your ADC with timers and make sure there's a firm time base is here we have our main loop, then we have a timer and an ADC. So in main, you can go set up your timer peripheral to go off at some period of time, right? Whatever it is, every second. And in that interrupt service routine, then you can go and say, okay, now take an ADC read, and then when that ADC's interrupt goes off, meaning that the conversion is done, you could go and read those things out. So here you have two ADC, or two interrupts that are part of this routine. So every time this goes off, it takes the ADC read, your ADC ISR goes off, and then you take that data and store it somewhere. You can't leave it here because there's just not enough room. There's only 5 registers basically to store stuff. So a lot of the task of an ADC is taking data and storing it in memory somewhere. The alternative mode that maybe some of you will do for your projects is that you have a timer, the timer setting up a time base, and you're going off, say, every second or maybe every couple, 100 microseconds. Goes off, you take an ADC read, and now in your timer ISR, you're telling DMA, you have a DMA controller, we'll talk about that later today or maybe next week, that, hey, when this ISR goes off, instead of me as a controller, as the main processor trying to do this, what I want is the DMA controller to take that data and store it off into memory. And this way, your core only has to wake up for this period of time to do this thing, and all that's automated and comes back and says, I'm done. And that done flag could be taken care of in your main loop, or it could just be another ISR that says, okay, take that data again. Yeah?
Is there any race conditions concerns with checking that DMA done?
Yeah. It can be bad. You can write bad software. It really depends on I might want to think about what's the condition here. There's no race condition in the sense that this done flag will only happen after the ADC has told DMA, hey, I have data for you, and then DMA is going to push it to the memory address you've told it to do. It's really, maybe your question is what do you do after this? Are you going to have a condition where it doesn't hit that timer again? Or maybe race conditions, the timer's gone off before this is done. That's reasonable as long as it's within your ADC time. But if this timer goes off faster than your ADC can converge, then yeah, you have the race condition. You can't get out of that. Does that make sense?
So what about just the main program just reading that bit DMA done?
It depends on what the goal is. If this is a repeating timer, you don't even care then, right? So what you'd have to do in this timer has to increment where DMA should write data from. So in your DMA, you say, hey, this is where I want you to get data, and this is where I want you to put data. So you just have to make sure that the pointer of where data should go keeps getting incremented. You don't want to overwrite that data. All right, so we can recap for ADCs. It's important to kind of realize the general type of ADCs and be able to reason about the trade-offs. I don't care if you can draw out the architecture of them, but you should be able to recognize the basic architecture and say, okay, why is a flash ADC faster than a slope integrator or faster than a successive approximation one? And you might have to be able to say, okay, this is an appropriate time to use this type of ADC. Not all your microcontrollers will have ADCs. There'll be times when you will be looking through data sheets trying to choose one that meets a certain task, and there are a lot out there, and here's the starting point of things to think about. And then your STM32 is a SAR ADC and provides you with a bunch of trade-offs, and then I just went through that part, but that's basically thinking through how can you use it and how can you use your timers and your DMA to get the most value or the get through ADC reads as fast as possible, if that's what you need for your application. All right. Any final questions about ADCs? Okay. Go on to DACs. So for DACs, we're going to talk about 3 major styles. Actually, we're going to talk about 4 styles of DACs. And then we'll talk about the STM. And then we'll talk about error types in ADCs and DACs that you should be aware of in general. So there's reading if you're interested. All right. So a DAC is essentially just a signal generator or a speaker, right? It is a thing that creates an analog value. The things you want to think about are just the opposites of ADCs. So you still think about, it's the opposite of an ADC, and you still think about size, speed and resolution and power dissipation and those sorts of facts. So the basic idea here, you're still going to use this binary ladder idea. You got some binary value here, and then through some process, you get an analog voltage out. Now, there's something slightly misleading about this. It's not that you get a time-varying analog voltage. It's for each digital value, you would get 1 point here, and then you change this digital value to get another point, another point, another point, another point. So you imagine you could be reading through a memory buffer, which basically just describes a waveform. So you could have triangle waves or square waves or whatever waves you want. And this DAC will be creating the analog values. And you can notice here, here's equations for the transfer function between a DAC value and an analog value. They're very similar, if not exactly the same as your ADC. It's just that the inputs and outputs have been switched, where instead of an analog voltage, you're trying to figure out the DAC. Here, you have a DAC voltage, and you're trying to figure out what the analog voltage is. We talked about sample and hold circuits for DAC or for ADCs, and now there's the same sort of issue in a sense with DACs. And this is this idea of a loading effect. And probably, if you're an embedded systems engineer, this should, before you graduate, the idea of a resistor and a load and this voltage divider thing should start feeling pretty intuitive. You find this happens, these sort of circuits and trade-offs happens all the time. And here we have a DAC that has some V desired, but it has some inherent source resistance. And that's limiting how much current can be pushed through. And depending on your loading condition, you can actually corrupt or change the V out voltage far enough away from the desired voltage to break your application. And so, as we talked about before, one way to get around that is you go put a voltage follower in there, basically an op amp, which will does not draw much current. So this will not let current go in here. It's equivalent high resistance, but it can drive lots of current out, so it can faithfully reproduce this value. We can see an example of that here. Just to drive this home, so I'll speed up the current. So here we can see that here we have, this is the output of a DAC, let's say. We're not talking about how this voltage is made at the moment. We're just saying here's the output of a DAC, and you can actually see the current flowing out. Here we have the same circuit, but you see there's no current flowing here because this is ideal situation, but it has high input resistance, which means it doesn't matter what current is going on here, it won't drag this down. Won't modify that. Now I'm going to go and change RL here, and you can see as I change this resistance, that voltage is going to change. Already it's not perfect. Right here it's 6.5 output. We're getting 6.5 here because we have this buffer in between. Here is 6.5, but now you have 5 volts out there. And so if we go and change your load resistance, right now I have a very large load, small resistor, but it's consuming lots of current. We actually saw current speed up, and you can see it's dragging down this voltage. So now my system's outputting 2.4 volts. I told it to do this, but the loading conditions have caused an error. And now I'm not getting the correct value on my output. Now, this one has this buffer in here, and it's still able to produce the correct value even though the load is fairly large.
Why did you do RL, the load, instead of RS, the
Well, why would I be changing R load? Because as engineers, you generally don't get much control over RS. RS is typically intrinsic, as you'll see. RS is intrinsic to the design. There's seats over there if you want, or up here. So this is going to be intrinsic to design, but my loading conditions, right? If you go put an LED on something, well, I'm going to load it down. I could put a resistor on something, right? That load is usually something that is changing.
So changing that load is what results in your voltage not being like the
Correct.
same.
Yeah, so here's a voltage divider, right? And so I've reduced this value, and now I can see my voltage divider has divided that down. If I make my load, like the ideal case would be, here, I'll make my load really large, 10K. Oh, that's great. Now, the difference between here and here isn't even that large. Maybe that's good enough for my application. But, oh, I wanted to drive a bigger load. Does anybody know what the input impedance of a speaker is? Guess people aren't making home stereos anymore. Anybody want to guess? Yeah.
Like 8 ohms?
8 ohms, exactly. I think, isn't cars like, it's like 8 ohms I think is for cars, and home stereos like 4 ohms or something. They're really small resistances. So now you think you've made this really whiz-bang amplifier, and you're just going to blast your neighbors out of the water. But here, this is at 600 ohms, and now you're dropping all this voltage, right? So now you have to do special techniques to be able to drive lots of current into that thing. Otherwise, look at the volume right here of my output of my speakers is small compared to what I wanted. We can also kind of see the effect of high source. First I'll show the effect of low source resistance. You always want low source resistance because now the top of your voltage divider is small. It doesn't really matter what this is. It's going to be pretty close. If my source resistance is small, life is pretty good. I can even make my load resistance. Right here I'm 800 ohms, and there's almost no difference because my source resistance is small. That would be great. Unfortunately, I can't really change my source resistance. As you see as you go up, right, 800 ohms, and I'm at 50% here. Now again, it didn't matter over here. Okay, any other questions? Yeah.
Can you go over that again, why we don't see current in the buffer? Yeah.
Magic. Now, for 373 students, op amps should just be magic. They shouldn't. Nobody wants to know how an op amp works. It's horrible. Whatever's inside of that, you're taking 311. You know what's inside of there? Is it horrible?
Yeah.
Can be. He's lying. It is horrible. Don't know what's inside of here. It's fine. What you do is you go find an analog engineer when you need it, op amp, or just follow some basic tutorials. If you just do normal tutorials and just do normal configurations, it'll be fine, especially if they're not fast. If you get into high frequency, then it becomes horrible. But anyways, you asked the real question. The real question here is that this does not accept current into it, right? It has high input resistance. That's what an ideal op amp is. So this breaks the loading condition. This is equivalent of like a mega ohm, and therefore it cannot load down this node, and because of this configuration, it's faithfully reproducing the input voltage. What? Magic. Okay. What other questions? You guys did voltage followers in 215, right?
Yes.
Like summing amplifiers? Okay. Great. Well, they're only good for fast applications if you take 311, and then the higher, like you gotta take a grad class before you learn that they're good for the higher applications. They're trying to get you to take more classes. All right. So now we talked about this idea that we're gonna have this buffer, and we'll talk about the most simplest DAC you could possibly make, and that is just a digital I/O pin putting out a PWM. This can make you a nice analog signal. It's going to sound horrible. That's fine. It's going to sound like you put it into a little piezo disc. It's going to sound like a buzzing sound, beep, 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 like an 8-bit Nintendo game, but that's fine. But it's cheap, right? All I had to do is put a resistor here and a comparator here, or a capacitor here, and I'll show you that I can turn these square waves into a sine wave. And the trick really is it's just going to be a low-pass filter. You're just low-pass filter, and you're taking this when you see here I'm mostly high, right? I'm very small, I'm a logical 0 here for a very short period of time, and my corresponding analog voltage is nearly VDD. And over here, right, I'm low most of the time, and for a very short period of time I have a little spike at VDD. So mostly of the time I'm at ground. You can see my corresponding analog value is pretty low. And this is just the fact that we're going to low pass filter that signal. And so you can go see a little fall stat about that. And here's where you'd want to have a little output buffer, because this thing can't load much down. That's the problem. So assume this is a microcontroller and it has internally buffered everything and everything's as nice as it can possibly be. You just won't be able to drive much load, so I put this little voltage follower here. But now we're going to control the duty cycle, and by controlling the duty cycle, I'm going to make the green line move up and down. And you can see that's just the output of this, and this node here is the output of my digital I/O pin. And so by changing the duty cycle, I'm charging up this filter basically, and now I have an analog voltage on the output that's higher. What do you think about that? Make a simple DAC. This is like you got like 12 hours before the demo. You're like, I just want to have some DAC points. I want to make a little buzz resistor capacitor. You fool around with that for a little while, you can make something buzz. And then to make an analog signal, right, you would just go in here and just vary this over time. And I'll even speed up the simulation a little bit to make it fast. And now, see? Now you can digitally make a sine wave or some tone that you can hear through a speaker. What do you think? Okay. She's like, I think that makes sense. Fantastic. I mean, there are problems here. Look, it's not a great signal because you're charging, your filter has to be designed for the frequency that you're at, and you get these ripples on top. So it's not going to sound great, but it's going to sound like something. Any questions? You guys are like, I made this already. I know this.
You're storing the value that you're putting in, like the digital value you're putting in, right?
I wouldn't say it's storing. This whole thing is acting like a low-pass filter. So it's going to low-pass filter this digital signal. And I'm going to change the duty cycle of this digital signal. And so the average of the duty cycle is what's going to come out here. And you can actually see this little RC charge up, charge down in between cycles. Here it's like charging up and then it charges down just for a little time. And so there's a bandwidth limitation here that this will only work well for certain frequency ranges. Right? If you go too fast, it's not going to work well. Yeah.
You're trying to minimize like distortion while we're
Yeah, but there's limitations. You can't get around it too much, right? So you're always going to have some amount of distortion on this thing, and there's other ways you could probably get around that to make a cleaner signal. This is just like cheap, rushed signals. But yes, we could do real math, like the electrical engineers would, calculate the correct size here for a duty cycle to minimize, like we can find those tutorials online. But we're computer engineers. We don't care about math anymore. We're just making stuff. All right, so any questions about, any more questions? All right, that's the simplest version. Now we're going to talk about resistor voltage divider. So this is basically going to be the inverse of a flash ADC. So how the flash ADC work? Remember, it had this resistor ladder, and then it was comparing the input voltage to all these nodes on the resistor ladder. Here we're going to do something slightly different. Here we have a reference voltage. All right, so that could be 3.3 volts or internal band gap, whatever it is. And then this ladder is going to make up a staircase of different analog values. And then you just go and connect one of them with a switch or transmission gate, connect one of them to an output stage, and then you're going to send that out. So then you'd have to have some decoder here, which is going to go through and select which one of them, but this is essentially just the exact opposite of a flash ADC. There's really nothing too special about it. Here we can see, remember, color here indicates voltage. So here we have ground, which is gray. We have green, which is 7 volts up here. And then we can see the gradations here. In fact, you can look, and a little down there, you can see 1 volt, 2 volts, so on and so forth. And then by putting a digital code in here, right, I'm going to select which one gets out here. And here, this is a binary decoding structure, right? But basically, it's a series of switches that's going to go through and connect that output value. So you can collect any value you want. Now it's going to give you some analog voltage on the output. Now, here the problem we're going to start seeing is there's no output buffer on this one yet. Right? So whatever load I put on here is going to be a function of all these resistors. And so some loads, like if I connected that one, oh, that one's not a great choice. Let's do this one. So this one would be 100 ohms divided over my load resistance. Well, 100 ohms is pretty small, so maybe that's not big a deal. But if I go here, now I have 700 ohms for this value. Yeah, about 700 ohms. And so now my output resistance is actually changing depending on what digital code I put in here. So another reason why you'd want to have an output buffer so that this structure doesn't change your output voltage. Does that make sense? You're like, no? No making sense? He's like, no. So if you're a computer scientist and you thought you wandered in the wrong class, totally fine. What do I want you to learn? What do I want you to know? First of all, just there's this structure that generates the voltage and that you're selecting them, and that there's this thing called output loading, and you just want to put an op amp here, whatever that magic op amp is, put out here to make sure it doesn't mess things up. That's all you got to know if you're a computer scientist. What do you think some of the drawbacks of this, other than the loading condition, which is solvable? What are some of the drawbacks of this type of DAC? Why don't you talk to yourself or talk with a neighbor, come up with 1 or 2 drawbacks of this type of DAC.
Simple. There's a drawback, and there's another drawback. You would have
This guy's reading in class.
He's got a smart for values, you'd have that larger.
Huge.
All of the resistances from these, it's like the resistance here, because of your voltage drop. That's crazy, because like some of the things. Said with the, if you do the place, there's like some shit that happens. It's like
Magic op amp.
Magic. It's green. All right, what do you think? What are some drawbacks of this type of DAC?
Maybe that's what's similar like flash EDC, you know, you have all these resistors that are supposed to be the same resistance, which you have to make sure that sort of maintain between like getting all those larger resistors in.
Yep, so while manufacturing this, all these resistances have to be the same or as close as possible, which is not trivial. It's a task, I mean, it's better, well, we'll show that it's better than trying to have precise values, but it's still hard to do. What else? Saw a hand back there. Yeah?
I was going to say there's a lot of components, so like high cost area.
Yeah, a lot of components, a lot of resistors, right? So the resistors make up area on a chip, and area costs money. So this one would, and you need a resistor for every single output value you have. So you're trying to get a 12-bit DAC. That's a lot of resistors, right? So now we're getting prohibitively expensive to make a DAC this style that has a lot of bits. But what's an advantage of this one? Any advantage? It's fast, right? Within one cycle, guaranteed. As long as you can, as fast as you can shut this gate, you can get the answer out. So one cycle, you can get conversions. Any other trade-offs? Let's see, I don't know, what do we got? Speed, area, linearity. I'm sure I'm missing something. Complexity. Takes a lot of switches, but only one op amp, which is kind of nice. But a lot of switches. Okay. A lot of resistors. All right, so there's, we'll go forward. So what happens if you took one of those switches and switched more than one switch at once? It seems like there could be some advantage there, so we can look through what that would be. So you may remember back to 215, we had this thing. It's terrible. I know it's terrible. The summing amplifier, magic box here. And remember what this does. A summing amplifier says I'm going to sum the current essentially going into this node. So sum this thing plus this thing plus this thing. I'm going to give you a proportional value over there. Very nice. So here's if you have those resistors there, here's your equation. Basically, I'm going to add voltages together. So this is like, an add block in analog. And we can just look at, try and get an intuitive understanding of that. We don't have to get through all the details, but essentially, oh, you can't see that, okay. So these are just two time variant functions. One's a square wave, one's a sine wave. Typically you're just thinking about a DAC putting out one value at a time, but this is just showing you how a summing amplifier would work. And it could just be two DC values. But all that's happening here, just to convince you how a summing amplifier works, we have a sine wave plus a square wave, and this is just the superposition of both signals on top of each other. It summed the two signals together, magically, I promise. Okay, how do we feel? Summing amplifier just takes two values, or analog values, and adds them together. Again, this doesn't have to be sine waves, it could just be two DC values. You could do it point by point. Okay, so that's how a summing amplifier works. So we're going to take that basic building block and we're going to make, they call it the R by 2R ladder, or R2R ladder. Ooh, that looks horrible on my screen. But basically we're going to have a structure here with multiple resistor paths and current paths, and we're going to create the structure such that current is divided equally. So we have half the current, reference current, a quarter, an eighth, a 16th going down, and then we're going to combine these different amounts of current together to be able to get an analog value out. So I can take half a reference current value and a 16th of a reference current value, add them together to make up a particular analog voltage. And so now you could also just look at this reference function here, and you're saying here are the switches, and I'm just going to say, is this 1 or 0? If it's 1, I include this term. If it's 0, I don't include this term. And now you can see how you can combine all these values into an analog output voltage. So this is nice. Let's go through an example. So this is just a different reconfiguration of that. And you can kind of see this voltage or current division here that the circuit set up. I'll set up the, right? This is approximately going twice as fast as that. Maybe this is going half that, half that. You could actually, we could calculate it out. We could look at the actual currents, figure that if that's true. What do we got here? Yeah, it's about right. What is this? 160 is about 180, or sorry, this is 80 microamps, 40, so on and so forth. And so now we're going to take those currents and we're going to sum them at this node to give us a proportional voltage out. So now we've been able to reduce the number of resistors that we need. We didn't need a whole resistor ladder because we can use multiple resistor pairs at a time to sum them together to get us an analog voltage. So now we're using less resistors. What question do you have? Yeah.
Why is your voltage negative? Oh.
Smart students asking questions, because that's when we're trying to teach something. I could show you the whole thing. We could buffer it, and I can make a really complicated circuit design that gives you positive voltage, and it's horrible. We don't want to do that. This makes the circuit too hard. This is kind of like the classic way to show this. Trying to get the intuition. Not trying to learn how analog circuits work. Nobody wants to know that. Only he wants to know that. You just want to get the intuition that, hey, I can have these currents. They're each one of them is half of the previous current. So I have all these different current values to select from, and then I'll add them together up by that equation, and it's going to give me a proportional output voltage. And that allows me to have less resistors. Okay. What would be a disadvantage? Talk with your neighbor, come up with some disadvantages for this method.
It's really confusing and complicated. Correct. Because you have like a sample
That's why he drives. That's why he connects.
That's your feedback. 50.1K resistor.
Also, it's negative.
What's the question?
Voltage divider you put in your input. Like let's say you wanted.
It's negative because he's in the.
But if he just tied
it's gonna confuse you.
just tied
Ignore
his
it.
negative to the ground and just connected positive.
Yeah, but your circuitry becomes more complicated because you can't just feed it like that because then you need
The switches, so each needs independent control.
No, I know.
What you typically do is, you don't need this to go full scale.
This is gonna confuse all you guys.
Sort of thing, and then you stage which inverts it. You have a negative rail, like negative voltage on your microcontroller because it's hard to convert.
No, it's
Actually, this would be at a disadvantage because the numbers.
Don't look at that negative sign. Too scary. Don't look at it. So this is the idea, right? So I can go change this value here. By switching these things at different switches, I can change the output value. I should have said that before. Watch this. So what's a disadvantage of this? Anybody see any disadvantages? It's like no. What would this be easy to manufacture? Hard to manufacture?
It's complicated.
It's complicated, yeah.
Harder to manufacture.
Harder to manufacture. Here we need to have some resistor values here that are proportional. It's not all the same resistor value. I need to have 2 resistor values and make sure that all of them are precise. It's not that bad. It's just 2 different types of 2 values, but it's still harder than the other one to manufacture. Any other advantages or disadvantages? Yeah.
Is it possible that current consumption is higher than the other option?
That's a good question. I think typically you're going to have these analog circuits. They're going to be in like the nanoamps, picoamps. Like it is definitely higher than the other one. Is it on a system level pretty appreciable? Probably not. I'm going to say probably this or the compared op amp here. I mean is probably higher value than these. So it's approximately the same. Yeah.
It's like 10 cents more expensive because you have to pass it through an inverter if you want a positive voltage. Or
yeah, it could be a little bit more expensive. That one we'll say we had the other one should have had at least an output stage on it. So, but yes, the real thing would be gets more and more complicated to get this thing to be a positive voltage. Okay, so what are the disadvantages? I say it's going to be harder to manufacture. It's still nice. One advantage is it's ready immediately. That's nice, right? Within 1 cycle. Okay. This one is more efficient in terms of how many resistors we need, so we can get to larger bit values easier than we could with the inverse of the flash. I forget what we call that one. Resistor ladder version. Okay. And we'll go to the last one here. And this one might feel almost exactly the same. Instead of having those 2 resistors, we're going to use 1 resistor here to create that current, and each resistor is going to have a different value, and it's going to be R divided by 2 by 4 by 8. So instead of having 2 resistors, we have 1 resistor, which is nice. Okay, and here you can have that transfer function. Basically walk through this and kind of figure out, okay, here I use D instead of S as switches, but here's, you put a binary value in here. And the big idea here is by using ratios of resistors, we're able to reduce the need for as many resistors. So that's valuable. You can look how that one works. And this one's simpler, right? Here we just have our voltage ratios. We have some digital voltages coming in. This is either going to be 1 or 0. And then by selecting some digital value, I'm able to change the output voltage. Okay, so simpler, but I'll just give it away. The disadvantage here is that now I have to manufacture all these different resistances. And making that on chip is hard. Maybe it's easiest to make one resistor value on chip and make them matched across all the resistors. That's the easiest, but then you need a lot. And here you need the lowest amount of resistors, which is nice, but you need to have multiple different types. So now we have this scaling problem of like how easy is it to manufacture versus how big my DAC can be. So this would be, I could scale to a large bit size, but I'm going to have linearity problems. And then the other one, which is, the more extreme version here is, well, I am very linear, but it's hard to get that large bit sizes. And then in terms of that trade-off, this is somewhere in between where, okay, I only have 2 resistor values to get in a ratio, so this is a little bit easier to manufacture, and I can get to somewhere in between in terms of absolute bit values. So what questions do you guys have? Yeah.
The speed numbers, a considerable thing that you have to weigh of how fast, like how this would be slower than the ones.
Can you just say that again? Sorry.
Like in this case, since you're having to flip a lot of switches to get the value you want, it'll take more cycles. Is that like a considerable amount of time that takes?
I think you can all do all those switches in parallel. They don't have to be sequential. So I don't think I think they're all 1 cycle. All right, so I don't know why the printing got messed up. I don't know why it got put on the next column, but it doesn't matter. Work with your partner, try and think through the trade-offs between these different resistors, or sorry, these different DACs. There we go. Howdy. Lots of students here today.
Bits line up with the bits.
Okay.
Last time he said use it.
Thank you. You guys need one more? All right. Thank you. You got one?
Sure, I had 2 people doing it. I'm actually not making it anymore. It's already done.
PWM, the voltage provider, you have like a ton of resistors. It's just a binary weighted. You have like 4 resistors, and you can.
If I can just so many people's computer. Nobody would know.
Yeah.
It's like everything's automated. I would just tell people.
It's all not 1 cycle. This is not
Resolution,
but just very fast.
Yeah, what did I say?
But same.
Kind of agree with me.
Okay.
It kind of showed us in these. Yeah.
Wait, I say I think that's right.
It's like wheeling or something.
Speed is like no, it doesn't have to go through anything.
Yeah, bro, that was the hardest concept to choose.
It depends on the
Depends on the specific sensors.
Good thing about
EWM plus LPF high complexity because it's
using 4 DACs is how long it takes the output of our analytics.
any of them faster or slower.
I'm gonna say me, I don't know.
I'm gonna say low to high.
Wouldn't it be based on how much circuitry is in there?
No, because it's dependent on what you.
We say clock cycle.
Yeah.
All those
have LDR.
take 1 clock cycle to close those switches.
It sounds like all of the others are the same speed.
EWM, I do not.
We just one does. It's magic.
I'm gonna write magic.
Yeah, me too. Be the same amount of power.
Have like, this is the only reason this one might be higher is because we
Okay, but what generates
Oh,
it?
it's very bad. Power.
I think it's like compared to
The
linearity.
yeah, they're all one cycle.
Low linear.
I'm probably good with medium power.
Zero resistors. Just have a lot of resistors.
Because he kind of agrees.
What do you mean by linear?
Linearity is how many components, like for the.
Oh, I'm thinking I was thought it's like how good the output signal was.
What's the resolution?
No, they're not. No, they're not.
It's bad.
Yeah, sucks.
Any switch we can close.
Linearity or low linearity?
I'm gonna say all of these are fast.
I put them all as medium because I have no idea. Read that samples book. Yeah. Ooh, I see resistors. How many resistors do you have?
So that was binary when off that, right?
I might want to fall.
Shut the binary weight out.
The idea is incredibly
I don't know what it is.
but the complexity is the hardest.
The thing is, I don't want to do my homework. I want to plan a trip instead. So.
The PWM, there's 2 N resistors. There's N switches, right?
They charge it fast.
So I got rid of very easy.
Just made it.
Divided by 10 to the third, and that's what I rated everything.
Yeah, that's way slower.
I didn't realize this is all a kilo. Okay.
One resistor. All right, John.
You put that in English?
Linearity is best on binary.
Oh, the resolution?
I got
Resistors is probably the.
I think you have voltage divider and arch bar.
Everyone besides
The one that uses the most
To
power
get this,
probably has the
I have to
highest.
have lots and lots of resistors to get high resolution. And I can't produce, so for the same area, I can get high resolution with this version, because it takes less resistors.
That like makes sense.
Less resistors.
I think your linearity works higher.
Yes, for the same area.
Okay.
Yeah.
What did you mean by complexity?
With high power for
Manufacture or design itself?
Because there's one problem that you can actually get -20 on.
Yeah.
And lots of it didn't happen.
Really simple, but you said it's the hardest to actually.
Manufacture.
Yeah.
Okay, but to be fair, the -20, I think we get to the
I think you're teaching about
linearity like number.
You couldn't get
Linearity
is like phenomenal.
I guess that would go to binary.
So the other one, like, they
Yeah.
like fried everything.
Oh,
Make it.
get a lot of money for that.
I guess that's but maybe the just business. Yeah, I guess since it's all the same thing.
I don't know.
Do you remember if you just
So many people.
All right, let's go through some here. How about we'll start with resolution. And resolution, I mean like bit resolution. Like for the same area, which architecture is likely to give you the more possible bits of resolution? How can, which architecture gives you bigger range, essentially? What do we think? Or we'll start, range is where I start. Biggest depth field, or bit field. Let's look at binary weight. What do you think about these three? Which ones gives you the highest number of bits for the same area? Yeah. Binary weight. And if you look through, you just need less resistors to get the same thing. So that's a benefit there. And then it is the R2R ladder. You need twice as many resistors, but you still get a better value than this, where you need one resistor for every possible division. Now, this one is almost not comparable to these, this low-pass filter one. So what's the resolution? I don't know. I said medium. I don't know. I mean, it's also like, this is noisy from a time point of view. So there's probably better ways to really maximize the performance here, but I'm going to say I put a little star there, because I don't think it's really comparable to those things. What about speed? Yeah. They're all the same. Anybody have a slightly different opinion? Okay. You're saying this one's slow. What about these? They're all the same. I agree with that one. Let's see what past me said. Okay. I said that these are all fast because this takes one clock cycle to close those gates. Right? So you're just switching between different analog voltage values. And so let's just say it gets done in one clock cycle. This one, I'm going to say, is extremely slow because it takes many clock cycles to create a PWM. Remember, PWM, you have to have a timer. You got a clock that goes in, and then you got a prescaler. Then you have a timer that's going off, and every once in a while, that timer goes off to make a PWM go high or low. So if you think about all the complexity, all the time it takes to make a PWM signal, and the fact that you need multiple clock cycles for your low-pass filter to settle down, now you say this is extremely slow compared to these. Anybody believe that? Some people believe it. Some people think they're in the wrong class. Okay, so don't worry. Last analog class. Linearity. What do we think? Let's not worry about this one for a second. How do we think about linearity? And by linearity, I mean the likelihood that you put a digital value in here and the transfer function to the analog value is linear as you go through your digital space. What's the likelihood that you'll have errors? What do you think for these three designs? Which one's the most error prone? Yeah. Binary weighted. Yeah, the binary weighted, because you have to have all these different resistor values. And that means that if you look at the binary one, it was like half R, or like there's R, and there's half R, and a quarter R, and an eighth R, and a 16th R going onwards. And now if there's a little variation, like maybe it's 16.5 for that last one, and they're not all perfect ratios of each other, that means that your transfer function is going to have weird steps in it. So this one's the hardest, the most complex to make in terms of to manufacture and get good linearity. What about these two? What do we think here? Which one's has the best linearity about these two? I would say, yeah, the voltage divider version does. Because this one is the same exact resistor. If you're good at it doesn't even matter if you make a 100 ohm resistor and you're off by 10 ohms, it doesn't matter as long as you're off by 10 ohms on every single resistor. That doesn't matter. And it's easy when you're making silicon to have one device manufactured exactly the same each time. It's easier than trying to make multiple devices or multiple resistors all exactly a particular value. All right, so what did I say? What did I say? Yeah, that makes sense. RR, okay. There's the ratio and this ratio of N. Okay, I agreed with myself. I should have said that this one is, linear is lower than this one. I don't know why I said medium, but I would say that this one's lower than this one. And then linearity, this one's horrible, just because it's already varying so much. How about power? Which is the best? Yeah.
You're missing complexity in between.
I am missing. Ooh. Whoa. Well, fine. Oh boy, you're right, I am. All right, well, for power, so this is low. Why do I say this is low power? Oh, because this is all digital, and this does need analog stuff. But I said these are probably, in the grand scheme of things, power, about the same amount of power. I mean, there are slight differences. That this has more past the ground than this does, but those are pretty small. They each have an op amp on the output. I'd say this is just all digital, probably the lowest power. All right, yeah.
Why is PWM low power?
There's no analog components in here whatsoever. I guess you still need a output drive op amp. No, you don't even need it. You can just use your GPIO pin, either driving high or low. You don't need a comparator. You don't need an op amp.
It takes a lot of time.
Why is time important? I mean, yeah, I guess you could say it takes more time to get there, but given time, the same amount of integration time for everything. Let's assume that. So, you know, microsecond for here and microsecond for there. I'd say they're about the same. I'd say this is lower power than that. All right, we'll get to complexity last. I don't know where complexity went. Number of resistors. This is nice because this is extremely low. You just need one external one. You don't even care. But here you have, it's good to think about the number of resistors you have, number of switches you have, and how this decreases. And this is really the thing that's causing you cost, is the number of resistors, maybe complexity as well for the number of switches. What did I write for complexity? Just complexity. I just said complexity randomly. That's good. Which one's the most complex then? We'll take a vote. What do we think? What do we think? Is this the most complex? Let's raise your hand. Anybody put this one? Yeah? How about this one? This is more complex than this. This one had horrible multiple resistors. I didn't understand anything in there.
Even more resistors.
This one has less resistors.
Different values.
Yeah. I would say the complexity, these are both approximately equal. Voltage divider I felt was easy to understand. Probably hard to manufacture. And then the complexity, I guess, for this one is probably the lowest. All right, 3 minutes. There's a DAC on your device. I'll blast through this. You have two DACs, 8 and 12-bit output modes. You can buffer it's actually, there's a calibration register that tells you what the offsets are, so you can make sure you get an accurate output voltage. There's actually a sample and hold mode, which doesn't make sense. What does that mean? Because you're not sampling something. What it will do is you can output an analog value. There's a sample and hold circuit on the output. You can put the entire device to sleep, and it will hold that analog value. And then you can wake up, update your analog value, go back to sleep, if you needed that, if you cared, if you're doing something really low power. They're giving you all the tricks. Now I got 2 minutes left. Don't go, because I got to teach you something. I promise. This has the same quantization error, same inherent problems that the ADCs had. That you're going to do this thing where you're going to do this offset. They do the offset over thing so that you can get advantage of the highest bit. And your quantization error, how far off you are from your desired value, your analog values from your desired value, is going to be 1 LSB. And I guess these are for all, now we're getting into both ADCs and DACs. So if you're looking at error functions, what are the causes of error? What are the types of errors that can show up? There's offset error. This could just be that some of those, like the foot or tail resistor of a DAC or of an ADC is off, and now there's an offset on it. That one's pretty easy. This one you can just calibrate out. There's a called full-scale error, which is the slope is off in your function. So you can calibrate this out as well. Maybe that transfer function isn't linear because of some manufacturing error. You'll find that there's some offset error. The one that gets really hard is differential nonlinearity. Basically, the step size between steps isn't the same. And that would come in when that DAC, if you looked at those the binary weighted one, where the resistor values were slightly different, you can actually get different step sizes. And that doesn't sound like that big a deal, but there really are DACs that you could actually have such an error where it's got a negative error where actually this output value is greater than this output or smaller than this output value, even though the binary bit is higher. And so if you're ever doing controls and you're trying to control something with a DAC or an ADC, understanding the error types in your thing will affect your control loop, because now you could get stuck in this local minimum. And then the last one is integration error, where this is kind of like offset error, but you can say that there's a bias in part of your ADC ladder, which is pushing you up, and now you have some integration error, which will make your ADC control loops bad. And so the last cycle, it's just good to know that these types of errors can exist, and how will it occur? Well, if you're doing an FFT of something, which will happen, your ADC is sampling stuff, but you're going to get all these harmonics off of it, even though you say these harmonics don't exist. I take my analog probe out, right, and I measure the signal. I don't see the harmonics, but in my data, I do see the harmonics. That can come out just because of your ADC or your DAC is causing the problem, because your hardware is imperfect. All right. With that, I'll let you go. Just remember, you just have to know the basic trade-offs between the DAC types. All right, thank you. Oh, please turn in your